The temperature outside Thomas Mercer's cabin read -18 degrees Fahrenheit on that January morning in 1843, but inside, his bare feet touched floorboards that felt warm as summer stone. 50 yards away, the Henderson family huddled around a roaring fire that devoured their last cords of wood while frost still crusted the inside of their cabin walls. Before we begin, let us know in the comments where you're watching from, and if stories of frontier ingenuity move you, hit that subscribe button, because tomorrow's tale is even more remarkable than this one. The knock came just after dawn on January 12, 1843. Thomas Mercer opened his cabin door to find Robert Henderson standing in snow up to his knees, his face gray beneath his beard, his words coming in clouds of frozen breath. The Henderson cabin, built just last spring using standard methods, had become uninhabitable. Despite burning wood continuously for 3 days straight, the interior temperature had dropped so low that ice formed on the water bucket sitting 5 feet from their fireplace. Robert's wife Mary and their 2 children, ages 7 and 9, were wrapped in every blanket they owned, shivering violently even as the fire consumed log after log. They needed shelter, or they would not survive another night. Thomas pulled on his boots and followed Robert through the pre-dawn darkness. The walk of 50 yards seemed longer in the brutal cold. Wind cut through any gap in clothing. Exposed skin numbed in seconds. This was the kind of cold that killed people, the kind that made the Dakota Territory winters legendary even among frontiersmen who had survived Montana and Wyoming. When Thomas stepped inside the Henderson cabin, he understood immediately why they were in trouble. The fireplace was massive, taking up nearly a quarter of the cabin's interior wall space. Robert had built it oversized specifically to generate more heat. A fire blazed inside it, flames reaching up into the chimney, consuming split logs, at a rate that would exhaust their wood supply within days. But the heat from that fire rose straight up and out through the chimney. The air 5 feet from the fireplace was barely above freezing. The corners of the cabin were cold enough that frost patterned the interior of the log walls. Mary Henderson sat with both children pressed against her, all 3 wrapped together in a buffalo robe. She looked up when Thomas entered, and he saw the fear in her eyes. This was not discomfort. This was a family in genuine danger. Robert explained that they had been burning wood continuously since the temperature dropped 4 days earlier. They had gone through nearly 2 full cords, wood that should have lasted them a month. At this rate, they would run out in less than a week, and there was no possibility of cutting more timber in these conditions. The standing dead trees they relied on for firewood were buried in snowdrifts. The temperature was too extreme for sustained outdoor work. If they could not get warm, they would have to abandon the cabin they had spent all summer building and seek shelter elsewhere. Thomas studied the fireplace construction while Robert talked. The problem was obvious to anyone who understood how heat moved. The fireplace was designed like every other frontier fireplace, optimized for cooking and light rather than heating. The firebox was deep, allowing large logs. The chimney was wide, creating strong draft. But that same draft that made the fire burn hot also pulled the heated air straight up and out of the cabin. The family was feeding wood into a system that sent most of its heat directly into the winter sky. The cabin walls, built with standard notched log construction and moss chinking, leaked cold air through dozens of small gaps. Thomas returned to his own cabin with the Henderson family following behind. When Mary and the children stepped through his door, the difference was immediate and obvious. The interior was warm enough that Mary loosened the buffalo robe within minutes. The children, who had been shivering constantly, gradually stopped trembling. Robert looked around in confusion. Thomas's fireplace was smaller than his own. The fire burning in it was modest, consuming perhaps a quarter of the wood Robert had been burning. Yet the temperature inside felt at least 40 degrees warmer than the Henderson cabin, possibly more. Robert walked to the fireplace and held his hands toward it. The heat was pleasant but not intense. This fire should not be capable of warming the entire cabin to this degree. He examined the walls, looking for some obvious difference in construction. Thomas's cabin used similar log construction, similar chinking. The door was well fitted, but not remarkably different from standard builds. The mystery deepened when Robert realized that the warmth was not radiating primarily from the fireplace. The entire cabin felt evenly heated. Even the corners, typically the coldest spots in any frontier structure, maintained comfortable temperature. Mary settled the children near the fireplace and accepted the coffee Thomas offered. She asked the question her husband was thinking. How was this cabin staying so warm with such a small fire? Thomas had been expecting this question since the moment Robert knocked on his door. He had known that eventually someone would notice. The system he had built was not visible from casual observation, but its effects were impossible to miss once you spent time inside during winter. He gestured for Robert to follow him and walked to the center of the cabin floor. The floorboards beneath their feet were made of split logs, smoothed flat on top and fitted tightly together. Standard construction for a quality cabin. But Thomas knelt and pointed to a section near the interior wall. If you paid attention, you could feel warmth radiating upward from the floor itself. Not intense heat, but steady, constant warmth. Robert knelt beside him and placed his palm flat against the wood. The boards were noticeably warm to the touch, warmer than any floor he had ever felt. The heat was not coming from above, it was coming from below. Thomas explained that what Robert was feeling was the result of 18 months of planning, 4 months of construction, and a system that most settlers would consider insane if they understood how it worked. He had built something beneath this cabin floor that recovered heat normally lost up the chimney and stored it in the earth and stone below the living space. The floor itself had become a radiating surface, releasing warmth continuously even hours after the fire had died down to coals. It was this stored heat, this thermal mass, that kept the cabin comfortable while using a fraction of the wood other cabins consumed. Thomas had not invented the concept of heating from below. The idea had lived in his memory since childhood, planted there by his grandfather during a winter evening in Pennsylvania 28 years earlier. Thomas had been 11 years old, sitting beside the fireplace in his grandfather's house while the old man told stories of his time in Europe as a young soldier. The grandfather had served briefly in the French army during the final years of Napoleon's empire and had spent one winter billeted in an Italian town whose name Thomas had long forgotten. What Thomas remembered clearly was his grandfather's description of the Roman bathhouse ruins the soldiers had explored. The old stone buildings had channels built beneath their floors, passages that once carried hot air from furnaces. The Romans had heated entire buildings by warming the floors, creating comfortable spaces even in winter. His grandfather had described standing in those ruins, seeing the engineering that allowed heat to spread evenly through rooms without massive fireplaces in every space. The soldiers had marveled at the sophistication of a civilization that had disappeared more than 1,000 years before they were born. That story had seemed like fantasy to 11-year-old Thomas. Interesting but irrelevant to life in Pennsylvania. He had filed it away with other tales his grandfather told and thought little of it for years. But when Thomas moved west at age 24, and when he built his first cabin in Dakota Territory at age 26, and especially when he spent his first winter watching a fireplace consume cord after cord of wood while cold air still leaked through every wall gap, that childhood story resurfaced. He began thinking about the principle his grandfather had described: heat rising from below rather than radiating from one wall, warm floors instead of hot fireplaces, even heat distribution instead of burning heat near the fire and freezing cold in the corners. The more Thomas thought about it, the more sense it made for frontier conditions. Wood was not unlimited. Cutting, hauling, and splitting timber consumed enormous time and energy. A system that used less wood while providing better heat would be valuable beyond measure. But Thomas had no engineering training. He knew basic carpentry from helping his father build barns and sheds. He understood how to notch logs and build a functional cabin, but designing a heating system based on a childhood memory of Roman ruins was far beyond his knowledge. He would need to learn principles he had never studied. He would need to experiment with materials and methods that frontier construction never used. Most significantly, he would need to convince himself that the effort was worthwhile before he could convince anyone else. Thomas left Dakota Territory in April of 1841 with a specific purpose. Other trappers and settlers traveled to St. Louis to sell furs, buy supplies, and spend money on entertainment. Thomas went to learn. He had saved money from 2 years of successful trapping, and he intended to invest that money in knowledge rather than goods. The city had libraries, technical workshops, and men who understood engineering principles that were completely unknown on the frontier. Thomas planned to find those resources and extract every piece of information relevant to his obsession with underground heating. The St. Louis Mercantile Library allowed visitors to read technical books for a small daily fee. Thomas spent 12 days there, reading everything he could find about heat, thermal mass, and building construction. Most of the books were written for educated audiences and used terminology Thomas barely understood, but he worked through them methodically, taking notes in a journal he had brought specifically for this purpose. He learned that heat moved through conduction, convection, and radiation. He learned that different materials stored heat differently, with stone and earth holding warmth far longer than wood or air. He learned that the Romans had indeed built hypocaust systems, exactly as his grandfather had described, and that these systems had worked efficiently for centuries. But reading about principles was different from understanding application. Thomas needed to see heat systems in operation. He visited a foundry on the western edge of St. Louis and spent an afternoon watching how they managed heat from their furnaces. The owner, a German immigrant named Friedrich Hess, was initially suspicious of this frontier trapper asking technical questions. But Thomas's genuine interest and intelligent questions eventually won him over. Friedrich explained how they used brick channels to route hot air from the furnace to different parts of the foundry. He showed Thomas how they controlled airflow using dampers and how they prevented smoke from backing up into work areas. Thomas visited a brewery and studied their cooling system, which used underground chambers to maintain stable temperatures. He examined a wealthy merchant's house that had been built, with a basement furnace and metal ductwork routing warm air to upper floors. Each example taught him something about moving heat, controlling airflow, or using thermal mass. He filled his journal with sketches and notes, building a mental library of techniques that might be adapted to frontier conditions. The critical insight came during his final week in St. Louis. Thomas was examining a brick kiln used for firing pottery when he realized that the principle he needed was simpler than he had been imagining. He did not need elaborate ductwork or expensive metal components. He needed passages that could contain hot air long enough for that heat to transfer into surrounding material. On the frontier, he had abundant access to one material perfectly suited for creating such passages: logs. Thomas returned to Dakota Territory in late May of 1841 with supplies that confused every trader and settler who saw them. Instead of the usual powder, lead, coffee, and salt that trappers purchased, Thomas had invested in 3 large augers with bits ranging from 2 inches to 6 inches in diameter, 20 pounds of fire clay packed in wooden crates, a set of specialized chisels, 2 levels, 50 feet of hemp rope, and a collection of iron measuring tools, including a folding rule marked in increments of 1/8 inch. The total cost of these items exceeded what most trappers spent on supplies for an entire year. When Thomas arrived back at his cabin site, he found 3 other settlers camped nearby. James Burton, William Cass, and Henry Thorne had all established claims within 5 miles of Thomas's location. They were building cabins for the coming winter and had stopped by to see if Thomas wanted to partner on a group hunting expedition. Instead, they found him unloading equipment that made no sense for frontier living. James picked up one of the augers and asked what possible use a trapper had for a tool designed to bore holes through thick timber. Thomas explained that he planned to hollow out logs to create air passages for a heating system. The three men looked at each other with expressions that mixed confusion and amusement. William asked why anyone would hollow out perfectly good logs instead of burning them for heat. Thomas began explaining the principle of thermal mass and heat recovery, but he could see them losing interest before he finished 3 sentences. Henry interrupted to say that if Thomas was cold, he should build a bigger fireplace like sensible people did. The idea of burying heat underground struck all 3 men as the kind of impractical nonsense that got people killed on the frontier. James was more direct. He told Thomas that frontier survival required focusing on proven methods, not experimenting with complicated systems that would probably fail. A man could freeze to death while trying to reinvent heating. The smart approach was to build a solid cabin using standard techniques, cut adequate firewood, and tend the fire properly through winter. Anything more complex was dangerous self-indulgence. Thomas listened to this advice without arguing. He had expected skepticism. The system he planned to build would seem counterintuitive to anyone who had not studied heat transfer principles. Over the following weeks, as Thomas began his construction work, other settlers stopped by periodically to observe his progress. Each visit brought fresh mockery. When Thomas spent 4 full days selecting specific logs based on straightness and diameter, William commented that he was wasting time that should be spent on actual building. When Thomas began the laborious process of boring out the first log's interior, Henry watched for 10 minutes before declaring the entire project insane. A hollow log was useless as building material and wasteful as firewood. Thomas was creating something with no practical value. But Thomas continued working. He had committed to building this system, and mockery from men who did not understand thermodynamics would not deter him. He knew the principles were sound. He knew the Romans had made similar systems work for centuries. The challenge was adapting those principles to frontier materials and conditions. That challenge would require months of careful work, but Thomas had the time and determination to see it through. The logs Thomas needed could not be random timber cut from convenient trees. Every piece of wood that would become part of his underground duct system required specific characteristics that most frontier builders never considered. Thomas spent 2 full weeks surveying the forest within 2 miles of his cabin site before cutting a single tree. He was looking for eastern red cedar logs with particular properties that would determine whether his heating system succeeded or failed in the harsh Dakota winters. The first requirement was straightness. Most trees grew with some degree of curve or twist, acceptable for standard cabin. Construction where logs could be notched and fitted despite irregularities. But Thomas needed logs that were straight enough to create continuous air passages without restrictions or tight curves that would impede airflow. He walked through stands of cedar, sighting along trunks, rejecting 19 trees for every one that met his standard. The logs he selected had less than 2 inches of deviation across their entire 12-foot length. The second requirement was consistent diameter. Thomas needed logs that maintained approximately the same thickness from one end to the other. Taper was natural in trees, but excessive taper would create ducts with varying interior dimensions after hollowing. Thomas calculated that he could work with logs that tapered no more than 1 inch over 12 feet. This eliminated most of the available timber. Cedar trees that grew in dense forest conditions, competing for sunlight, often developed the straight, consistent growth pattern he needed. Trees that grew in open areas with abundant light tended to develop more taper and irregular branching. The third requirement was size. The logs needed to be large enough that hollowing them out would still leave walls thick enough to maintain structural integrity. Thomas determined that logs with a minimum diameter of 14 inches would work. After boring out a 6-inch diameter passage through the center, that would leave 4 inches of wood wall thickness on all sides. Thinner walls might crack or collapse under the weight of earth and floor materials that would be placed above the buried ducts. The fourth requirement, and perhaps most critical, was wood quality. Cedar was naturally rot-resistant, containing oils that prevented decay even in contact with moisture. This property made cedar ideal for underground installation where the logs would be surrounded by earth that held dampness. But not all cedar was equally resistant. Thomas looked for trees growing in well-drained soil rather than low-lying wet areas. Trees stressed by poor growing conditions produced wood with less of the protective oils. Thomas tested each candidate tree by cutting a small sample and examining the color and smell of the heartwood. Dense aromatic heartwood indicated high oil content and superior rot resistance. By the end of his 2-week selection process, Thomas had identified 8 cedar trees that met all his requirements. He felled them carefully, cutting them to exact 12-foot lengths. Each log weighed approximately 400 pounds. Moving them from the forest to his cabin site required building a simple sled and using his horse to drag them one at a time. The entire selection and transport process consumed 3 weeks of work before he could begin the actual hollowing process. James Burton stopped by during the hauling phase and commented that Thomas had spent more time selecting 8 logs than most men spent building entire cabins. Thomas began hollowing the first cedar log on June 17, 1841. The process he had designed combined 3 different techniques, each addressing a specific challenge in creating a smooth, consistent passage through 12 feet of solid wood. The work was tedious, physically demanding, and required absolute precision. A single mistake could ruin a log that had taken days to select and transport. Thomas worked slowly, measuring constantly, and accepting that this phase of construction would consume most of his summer. The first step was marking the center line. Thomas used his folding rule and a length of string coated with charcoal dust to snap a perfectly straight line down the entire length of the log. This line would guide all subsequent drilling and ensure the passage remained centered. He marked the line on both ends of the log and at 2-foot intervals along its length, using a square to verify that the marks aligned precisely. Any deviation from center would create weak spots in the wall thickness or cause the passage to break through the exterior surface. The second step was the initial boring. Thomas used his largest auger, a 2-inch bit mounted on a handle that required both hands to operate. He positioned the log on a framework of smaller logs that held it stable and at working height. Starting from one end, he bored into the log, using his marked center line as a guide. The auger bit cut slowly through the dense cedar, requiring 30 to 40 full rotations to advance 1 inch. Thomas had to stop every few inches to clear wood shavings from the bit. Boring the complete 12-foot length with the 2-inch auger took 6 full days of continuous work. The third step was enlarging the passage. Thomas switched to his 4-inch auger and repeated the entire boring process, following the pilot hole created by the smaller bit. The larger auger was significantly harder to turn, requiring Thomas to use a wooden crossbar inserted through the handle for additional leverage. The 4-inch boring took 9 days to complete. By the end of this phase, Thomas had a passage approximately 4 inches in diameter running through the log, but the interior surface was rough, showing spiral marks from the auger bit and occasional tear-out where the bit had caught the wood grain. The fourth step was smoothing and final enlargement. This phase used a technique Thomas had developed after considerable experimentation. He built a small, controlled fire inside the passage, using the heat to char the interior surface. The charred wood could then be scraped away using long-handled scrapers he had fashioned from iron straps. By repeating this charring and scraping process multiple times, Thomas gradually enlarged the passage to 6 inches in diameter while creating a smooth, consistent interior surface. The charred surface also had a beneficial side effect. It was harder and more resistant to moisture than raw wood would be. The final step was sealing. Thomas mixed his fire, clay with water to create a thin slurry, and applied it to the interior surface using a long-handled brush made from horsehair. The clay sealed any small cracks or imperfections and created a smooth, airtight surface that would prevent smoke from seeping through the wood walls into the surrounding earth. With 4 hollowed logs completed by mid-August, Thomas began the most physically demanding phase of his construction. He needed to excavate trenches beneath what would become his cabin floor, creating a carefully designed pathway for the underground ducts. The excavation required removing approximately 8 cubic yards of earth while maintaining precise depths and slopes that would ensure proper airflow and drainage. This was not simple digging. Every measurement mattered. Every angle affected how the system would function once buried and covered. Thomas had already built the cabin's foundation walls using standard log construction. The structure stood empty, waiting for floor installation. Now he worked inside those walls, marking trench locations with stakes and string lines. The design called for 2 parallel trenches running the length of the cabin, each 12 feet long, positioned 4 feet apart. The trenches would be 2 feet wide and 18 inches deep at the fireplace end, sloping gradually to 24 inches deep at the far end. This 6-inch drop over 12 feet would create natural convection, encouraging hot air to flow through the system. Thomas began digging on August 19th. The soil was a mixture of clay and sandy loam, moderately easy to excavate, but prone to collapsing if the trench walls were not cut cleanly. He used a narrow spade to cut vertical edges and a flat shovel to remove material from the trench bottom. Every 6 inches of depth, he checked his level to ensure the slope remained consistent. The work was slow and methodical. He excavated approximately 8 inches of depth per day, carefully shaping the trench as he went deeper. By August 27th, both trenches were complete. Thomas had removed all the excavated earth from the cabin interior and used it to build up the ground level outside, improving drainage away from the foundation. The trenches were clean, uniform, and precisely sloped. But before installing the hollowed logs, Thomas added a critical feature that would determine the system's long-term durability. He lined the bottom of each trench with a 4-inch layer of crushed stone, small rocks he had gathered from a nearby creek bed and broken to uniform size. The stone layer served multiple purposes. It provided drainage if any moisture accumulated in the trenches. It created a stable, level base for the heavy cedar logs. Most importantly, it would prevent the logs from sitting directly in contact with soil, reducing rot potential despite the cedar's natural resistance. Thomas had learned from his St. Louis research that even rot-resistant wood eventually degraded when buried in constantly damp earth. The stone layer created an air gap and drainage path that would keep the log bottoms relatively dry. The final preparation step was compacting the stone. Thomas used a heavy wooden tamper, essentially a log section with handles, to pound the stone layer until it was firm and level. He checked the slope again, confirming that the stone layer maintained the same 6-inch drop from fireplace end to far end. The trenches were ready. The next phase would be installing the hollowed logs and connecting them to create continuous air passages beneath the cabin floor. The fireplace Thomas had built into his cabin's north wall followed standard frontier construction in most respects. River stone foundation, clay mortar, firebox size to accept logs up to 3 feet long, and a chimney that extended 4 feet above the roofline. But Thomas had incorporated one non-standard feature during the initial construction, a feature that now became critical for his underground heating system. The firebox had a secondary opening at its base, a rectangular passage 8 inches wide and 6 inches tall, built into the back wall behind where the fire would burn. This passage connected the firebox to the beginning of his underground duct system. During normal fireplace operation, smoke and hot air would rise naturally up the chimney. But Thomas intended to capture some of that heat before it escaped, routing it through his buried cedar logs where the thermal mass of earth and stone could absorb and store the warmth. The challenge was creating this heat capture without disrupting the chimney's draw or filling the cabin with smoke. Thomas had studied this problem extensively during his time in St. Louis. The foundry owner, Friedrich Hess, had explained that controlling hot air movement required understanding pressure differentials and airflow dynamics. Hot air rose because it was less dense than cold air. A chimney worked because the column of hot air inside created lower pressure at the base, pulling in more air to feed the fire. If Thomas tried to force all the hot air through his underground ducts, he would eliminate the chimney draw and the fire would not burn properly. The solution was creating a split-flow system. The chimney would handle the majority of exhaust, maintaining proper draw and fire operation. The secondary passage would capture a smaller portion of the hot air, perhaps 20 to 30% of the total volume, and route it underground. Thomas designed a damper system using a flat stone that could slide partially across the secondary passage opening. By adjusting this stone's position, he could control how much hot air entered the underground ducts versus how much went straight up the chimney. Installing the transition from fireplace to underground duct required precise fitting. Thomas had positioned his first hollowed cedar log so its opening aligned exactly with the secondary passage in the fireplace base. He built a transition chamber using small flat stones and clay mortar, creating a sealed connection between the fireplace opening and the log's entrance. The chamber was designed to prevent any smoke leakage into the cabin interior while allowing hot air to flow smoothly from the firebox into the buried duct. The critical test came on September 4th when Thomas lit his first experimental fire. He started with a small fire, just enough to generate modest heat and smoke. He watched carefully as smoke began rising up the chimney while simultaneously entering the secondary passage. The flow seemed balanced. The fire burned cleanly without backdraft. He adjusted his damper stone, restricting the secondary passage slightly, and observed how the fire responded. The flames remained strong and steady. Over the next 3 days, Thomas conducted multiple tests with fires of varying sizes. He learned that the damper needed different positions depending on outside temperature and wind conditions. He discovered that the system worked best when the secondary passage handled approximately 1/4 of the total exhaust volume. The hollowed cedar logs lay in their stone-lined trenches, positioned end to end to create 2 parallel passages running the length of the cabin. But the logs were separate pieces, not continuous tubes. Where each log ended and the next began, there was a joint that would leak hot air if not properly sealed. Additionally, the logs themselves, despite Thomas's careful clay coating of their interiors, still had the potential to allow some smoke seepage through the wood grain into the surrounding earth and potentially into the cabin's living space. Thomas needed a sealing method that would create airtight passages capable of containing hot smoke under pressure. The solution required materials that most frontier cabins never used. Thomas had brought fire clay from St. Louis specifically for this purpose, but clay alone would not be sufficient. He needed a compound that combined flexibility, adhesive strength, heat resistance, and impermeability to smoke. After considerable experimentation during late August, he had developed a mixture that met all these requirements. The formula combined fire clay, sand, horsehair, pine resin, and linseed oil in specific proportions. The base ingredient was fire clay, a type of clay that could withstand high temperatures without cracking or degrading. Thomas mixed the clay with fine sand in a ratio of 3 parts clay to 1 part sand. The sand prevented the clay from shrinking excessively as it dried, reducing crack formation. He added horsehair, cut into lengths of approximately 1 inch, to the clay-sand mixture. The hair acted as reinforcement, similar to how it strengthened the chinking between cabin logs. The hair prevented cracks from propagating through the dried compound. The pine resin came from trees Thomas had tapped specifically for this purpose. He had collected raw sap during early summer and boiled it down to remove water and volatile compounds, leaving behind a thick, sticky resin. This resin made the mixture waterproof and gave it strong adhesive properties. Thomas heated the resin until it liquefied, then mixed it into his clay-sand-hair combination while everything was still warm. The heat made the materials blend thoroughly, creating a uniform compound. The final ingredient was linseed oil, which Thomas had purchased in St. Louis. The oil increased the mixture's flexibility and workability. It allowed the compound to remain slightly pliable even after drying, accommodating the minor expansion and contraction that would occur as the buried logs experienced temperature changes. Thomas added the oil last, kneading it into the mixture until the consistency resembled thick bread dough. Applying the sealing compound required working in sections. Thomas started at the fireplace end where the first two logs joined. He packed his compound into the joint, forcing it deep into the gap between log ends. He built up the compound until it formed a collar approximately 4 inches wide around the joint's exterior. Then he reached inside the passage with a long wooden paddle and applied compound to the joint's interior, creating a smooth transition that would not impede airflow. Each joint took approximately 3 hours to seal properly. Thomas worked on the 8 joints connecting his logs over 4 days, allowing each seal to begin setting before moving to the next. The compound dried slowly, taking nearly a week to reach full hardness. During this curing period, Thomas checked each joint daily, applying additional compound to any spots that showed shrinkage cracks. The underground duct system was complete and sealed, but Thomas had designed one additional element that would maximize heat distribution throughout the cabin's interior space. Above the buried logs, at the point where the ducts terminated at the far end of the cabin, he planned to build a stone platform that would serve as a thermal mass collector and radiator. This platform would sit directly above the duct exits, absorbing heat from the air flowing out of the passages and storing that warmth in hundreds of pounds of river stone. Thomas began gathering stones in mid-September, selecting them from a creek bed 2 miles from his cabin. He needed flat stones approximately 6 to 10 inches across, uniform enough to stack in stable layers, but irregular enough that air could circulate between them. Over 5 days, he hauled nearly 800 pounds of stone, carrying them in a canvas sack that held about 60 pounds per trip. The work was tedious but necessary. The thermal mass principle required significant weight of stone to store meaningful amounts of heat. The platform design called for a rectangular structure 4 feet long, 3 feet wide, and 18 inches tall, positioned at the terminus of his underground ducts. Thomas built it in layers, starting with larger stones at the base and working upward with progressively smaller pieces. He used no mortar. The stones were simply stacked with careful attention to stability, creating gaps between them that would allow hot air exiting the ducts to flow through the entire stone mass before escaping into the cabin. The bottom layer sat directly over the duct exits. Thomas had extended both cedar logs so they terminated beneath where the platform would stand. He left the log ends open, allowing hot air to flow freely upward into the stone mass. As he stacked subsequent layers, he angled stones to create channels that would distribute air throughout the platform rather than allowing it to simply shoot straight up through one path. The completed platform was substantial, weighing approximately 700 pounds. Its mass meant it would heat slowly but retain warmth for extended periods. Thomas calculated that once the stones absorbed heat from several hours of fire operation, they would continue radiating warmth into the cabin for 12 to 15 hours afterward. This extended heat release was the core advantage of thermal mass heating. A traditional fireplace stopped producing warmth minutes after the fire died. Thomas's system would keep the cabin warm through an entire night. The final construction step was installing floorboards over the entire cabin interior. Thomas used split logs, flattened on one side, and fitted tightly together. He left the floor loose, not nailed down, positioned over the buried ducts and stone platform. The boards rested on support beams that spanned the cabin width, creating an air gap of approximately 2 inches between the floor surface and the earth below. This gap was intentional. It would allow heat radiating upward from the buried ducts and stored in the earth to warm the floorboards from beneath, turning the entire floor into a radiating, heating surface. On September 23, 1841, Thomas lit the first full-operation fire in his modified fireplace. He had conducted small test burns to verify the damper system and check for smoke leaks, but this would be the first attempt to run the complete underground heating system under realistic conditions. The morning temperature was 48 degrees, cool enough that heat would be welcome, but not so cold that Thomas would suffer if the system failed completely. He built the fire using standard technique, starting with kindling and small splits, gradually adding larger pieces as the fire established. The flames caught quickly and grew to fill the firebox. Smoke rose up the chimney in a steady column. Thomas watched the secondary passage at the firebox base where hot air should be entering his underground duct system. For the first few minutes, he saw nothing. Then, as the fire grew hotter, he noticed a shimmering in the air near the passage opening, the visual distortion that indicated hot air movement. Thomas walked to the far end of the cabin where his stone platform sat above the duct exits. He knelt and held his hand near the gaps between stones. Warm air was flowing upward, not intensely hot, but noticeably warmer than room temperature. The system was working. Hot air from the fireplace was traveling through 12 feet of buried cedar logs and emerging at the platform. He adjusted his damper stone, partially closing the secondary passage to reduce flow. The warm air from the platform decreased. He opened the damper wider, and the flow increased. The control mechanism functioned as designed. Over the next 4 hours, Thomas maintained a moderate fire and monitored the system's behavior. He observed several phenomena that confirmed his theoretical understanding of thermal mass heating. First, the floor gradually became warmer. Initially, only the area directly above the ducts felt warm, but after 2 hours, warmth had spread to encompass most of the floor surface. The heat was transferring from the buried logs into the surrounding earth, and that earth was radiating warmth upward through the floorboards. Second, the stone platform became hot to the touch. The hundreds of pounds of river stone were absorbing heat from the air flowing through them. Thomas could feel the stored energy when he placed his hand on the upper stones. This thermal battery would release its warmth slowly over the coming hours. Third, the cabin's interior temperature had risen significantly despite the modest fire size. Thomas estimated the interior was now 25 to 30 degrees warmer than outside, a differential achieved with perhaps half the wood a standard fireplace would require. The real test came that evening. Thomas let his fire die down to coals around sunset. In a traditional cabin, this would mean rapidly dropping interior temperatures as heat stopped being generated. But Thomas's cabin behaved differently. The floor remained warm beneath his feet. The stone platform continued radiating heat. The cabin temperature dropped slowly, far more slowly than natural cooling would predict. By midnight, 6 hours after the fire had effectively gone out, the cabin interior was still comfortable enough that Thomas needed only a single blanket for sleeping. William Cass arrived at Thomas's cabin on an October morning when frost covered the ground and temperatures hovered just above freezing. William had been working on his own cabin 5 miles west and had come to borrow an auger, ironically, one of the tools he had mocked Thomas for purchasing months earlier. When Thomas opened his door, William noticed immediately that Thomas was wearing only a shirt despite the morning cold. Inside William's own cabin that morning, he had been bundled in a coat while trying to coax his fireplace to life. William stepped inside and stopped. The cabin was warm, genuinely warm, not the marginal warmth of a space barely protected from outside cold. Thomas's fireplace had only a small fire burning, flames consuming. A single split log, yet the interior temperature felt at least 40 degrees warmer than outside. William looked around, trying to understand what he was experiencing. He saw nothing unusual, standard log walls, normal chinking, regular floorboards. But his feet felt warmth through his boot soles, warmth radiating upward from the floor itself. Thomas explained the system while William examined the stone platform and walked the length of the cabin feeling the warm floorboards. William's skepticism gradually transformed into confused respect. He could not deny what his senses reported. This cabin was warmer than seemed possible given the small fire burning. Thomas showed him the damper system, explained the buried ducts, described the thermal mass principle. William listened, but struggled to fully comprehend how burying heat underground resulted in a warmer cabin. Word of Thomas's success spread through the scattered settler community over the following weeks. James Burton visited, then Henry Thorne, then others whose cabins were within a day's travel. Some came skeptical and left convinced. Others remained doubtful even after experiencing the warmth firsthand, attributing it to some trick or temporary condition rather than accepting that Thomas's complex system actually worked better than traditional methods. But whether they believed in the principle or not, none could deny the observable result. Thomas's cabin stayed warmer while burning less wood than any comparable structure in the territory. The most telling reaction came from a trapper named Douglas Webb, who spent an entire afternoon measuring the wood Thomas burned compared to the heat produced. Webb had spent 15 years in the mountains and considered himself an expert on frontier survival. He examined every aspect of the cabin, searching for some hidden fire source or insulation trick that would explain the warmth. Finding none, he finally admitted that Thomas had accomplished something genuinely innovative, though Webb still insisted the labor investment was too extreme for most settlers to justify attempting replication. The first significant cold arrived on October 19th, earlier than most settlers had expected. The temperature dropped to 28 degrees overnight, and a north wind made conditions feel even colder. This was the kind of weather that separated adequate cabins from inadequate ones, the first real test of how structures would perform during the brutal winter months ahead. Settlers throughout the region woke that morning to cold cabins and began burning wood at rates they knew were unsustainable if such temperatures persisted. Thomas woke to a cabin that felt comfortable despite the overnight temperature drop. His fire had burned down to coals hours before dawn, yet the floor beneath his sleeping platform still radiated warmth. He rekindled the fire using kindling and a single split log, a fraction of the wood his neighbors were consuming to heat their spaces. Within 30 minutes, his cabin had returned to the warmth levels he had maintained throughout October. The system was performing exactly as his thermal mass calculations had predicted. William Cass was not so fortunate. His cabin, built using traditional methods with a large fireplace designed to generate maximum heat, had become uncomfortably cold overnight. He had burned through 6 split logs, trying to warm the space that morning, yet cold air still leaked through gaps in his chinking, and the heat from his fire rose straight up the chimney. By mid-morning, William had made a decision. He rode to Thomas's cabin and asked for help building an underground duct system. Thomas agreed, but explained that the work could not be rushed. Building the system properly required hollowing logs, excavating precise trenches, and modifying the fireplace, all tasks that would take weeks even with 2 men working together. William's cabin was already built, which meant they would need to tear up his existing floor, excavate beneath it, and reinstall everything after the ducts were in place. The disruption would be significant. William understood but insisted the effort was worthwhile. He had experienced both systems firsthand. The difference was undeniable. Over the next 2 days, 3 more settlers approached Thomas with similar requests. The October cold snap had revealed the limitations of standard frontier heating methods. Men who had mocked Thomas's elaborate construction during summer now wanted to replicate his techniques. Thomas was willing to help, but he made clear that each installation would require substantial time and effort. He could not build these systems for others. He could only teach the principles and techniques, then assist with the most difficult phases of construction. James Burton was among those who sought Thomas's help. James had been the most vocal skeptic during the summer, calling Thomas's project a waste of resources. Now, after spending 2 nights burning excessive wood, while his family still shivered in their cabin, James admitted he had been wrong. The underground heat recovery system was not theoretical nonsense. It was practical engineering that solved a real problem. James asked if Thomas would be willing to demonstrate the log hollowing technique and explain the trench design specifications. Thomas agreed, and over the following weeks he would teach 5 different settlers how to build their own versions of his heating system. The winter of 1841 to 1842 was severe, even by Dakota Territory standards. Temperatures dropped below 0 Fahrenheit multiple times between November and March. But the defining weather event came in mid-January, a blizzard that arrived with little warning and created conditions that tested every cabin in the region. The storm began on January 9th, with light snow and moderate winds. Within 6 hours, it had intensified into a full blizzard, with temperatures dropping to -18 degrees and winds strong enough to create drifts that buried anything less than 5 feet tall. The blizzard lasted 3 days. During that time, leaving a cabin meant risking death from exposure. Settlers who had adequate wood supplies and effective heating systems survived the storm uncomfortably but safely. Those whose cabins were poorly built or whose wood supplies were insufficient faced genuine danger. The Henderson family, whose cabin Thomas had visited the previous January, had rebuilt using some of Thomas's techniques, but had not installed underground ducts. Their improved cabin was better than their original structure, but still inadequate for the extreme conditions. By the second day of the blizzard, they had burned through most of their wood supply trying to maintain livable temperatures. Thomas's cabin performed remarkably during the storm. He maintained a moderate fire throughout the 3 days, burning approximately 1 cord of wood total. The underground duct system and thermal mass heating kept the interior temperature stable between 60 and 65 degrees Fahrenheit, despite the -18-degree exterior temperature and brutal wind. The floor remained warm enough that Thomas could walk barefoot comfortably. The stone platform radiated steady heat that required no constant fire tending. He let the fire die down to coals overnight and rekindled it each morning with minimal effort. On the 3rd day of the blizzard, during a brief lull in the wind, Robert Henderson fought through waist-deep snow to reach Thomas's cabin. His family had run out of firewood. Their cabin interior had dropped below freezing. Mary and the children were showing early signs of hypothermia despite being wrapped in every available blanket and buffalo robe. Robert needed shelter, or his family would die. Thomas immediately agreed to take them in. Robert made 2 trips through the dangerous conditions, first bringing Mary and the children, then returning for what supplies he could carry. The Henderson family spent 4 days in Thomas's cabin while the blizzard continued and then slowly abated. During that time, 6 people occupied a space designed for 1, yet the heating system maintained comfortable temperatures throughout. Thomas burned slightly more wood to compensate for the additional body heat loss from 6 people instead of 1, but the increase was modest. He estimated he used perhaps 50% more wood than normal, far less than would be required to heat a standard cabin for 6 people during such extreme cold. When the weather finally cleared enough for travel, Robert Henderson asked Thomas to help him build an underground duct system in the cabin Robert would construct to replace the one that had failed his family. Robert Henderson's request represented something more significant than one man asking for building advice. It marked the moment when Thomas's heating innovation transitioned from individual experiment to community knowledge. Robert had experienced both the failure of traditional heating and the success of thermal mass systems during the most dangerous weather conditions frontier life could present. His family had survived only because Thomas's cabin could maintain warmth that should have been impossible given the wood consumed. Robert understood with complete clarity that building technique was not a matter of preference or style. It was a matter of survival. Thomas agreed to help but established conditions. He would not build Robert's system for him. He would teach Robert the principles, demonstrate the techniques, and assist with phases that required two people or specialized knowledge, but Robert would do the majority of the work himself. This approach served two purposes. First, Thomas had his own work to accomplish and could not spend months building heating systems for others. Second, and more importantly, Robert needed to understand every aspect of the construction so he could maintain and repair the system over years of use. They began in early March when weather permitted outdoor work. The first phase was selecting and felling appropriate cedar trees. Thomas took Robert into the forest and explained what characteristics made logs suitable for hollowing. They spent a week identifying 8 trees that met the requirements for straightness, diameter, consistency, and wood quality. Robert cut the trees himself under Thomas's supervision, learning to fell them without splitting the trunks and how to cut them to precise 12-foot lengths. The hollowing process took Robert nearly 6 weeks. Thomas demonstrated the technique on the first log, showing how to maintain centerline alignment and how to use the augers without wandering off course. Robert completed the remaining 7 logs working alone, though Thomas checked his progress every few days and corrected errors before they became irreparable. The work was tedious and physically exhausting, but Robert persisted. He remembered watching his children shake with cold in their inadequate cabin. That memory provided motivation through the long hours of boring and scraping. While Robert worked on hollowing logs, Thomas helped him excavate the trench system in his new cabin. This phase required precision that Robert had not yet developed. Thomas laid out the trench locations, established the proper slope, and supervised the digging to ensure dimensions remained consistent. They worked together for 2 weeks, with Thomas teaching Robert how to check level and grade, how to line trenches with stone, and how to compact the base properly. The fireplace modification was the final phase where Thomas's expertise was critical. Robert had built a functional fireplace, but creating the secondary passage and damper system required understanding of airflow dynamics that Robert lacked. Thomas spent 3 days working with Robert to retrofit the fireplace, explaining why each dimension mattered and how to test the draw before finalizing the installation. By late May, Robert's cabin had a complete underground heating system built to the same specifications Thomas had developed. Over the following 5 years, Thomas's underground heat recovery technique spread throughout the northern Dakota Territory and into parts of Montana and Minnesota. The dissemination was organic and unplanned. Thomas never promoted his innovation or sought recognition for developing it. He simply shared his knowledge freely with anyone who asked, and those who built successful systems shared their knowledge with others. By 1846, an estimated 40 to 50 cabins in the region incorporated some version of the buried duct heating method. The technique evolved as different builders adapted it to their specific circumstances and available materials. Some settlers who lacked access to large cedar logs used stone channels instead, building underground passages from flat rocks mortared together. Others experimented with different trench depths, discovering that deeper installation provided more thermal mass but required more excavation labor. A few innovative builders created systems with multiple ducts branching from a single fireplace, distributing heat to different areas of larger cabins. William Cass developed a variation that used shorter duct runs but incorporated a larger stone platform, emphasizing thermal storage over heat distribution distance. His system worked well for his smaller cabin and required less log hollowing, making it faster to build. James Burton designed a system that included an above-ground stone bench positioned over the duct exit point, creating a warm seating area that absorbed and radiated heat. These variations maintained the core principle of capturing fireplace heat in thermal mass while adapting the specific implementation to individual needs. Not every settler who attempted to build the system succeeded. The construction required precision and patience that some builders lacked. Improperly sealed ducts leaked smoke into cabins, creating dangerous conditions. Inadequately sloped trenches failed to maintain proper airflow. Poorly selected logs cracked or rotted after burial. These failures reinforced the importance of understanding the underlying principles rather than simply copying the visible elements. Thomas found himself teaching not just construction techniques, but the physics of heat transfer, the properties of different materials, and the importance of precision in execution. The Dakota Territory community began referring to cabins with underground heating as Mercer systems, naming them after Thomas despite his lack of interest in credit or recognition. The name stuck even as variations diverged from his original design. A warm floor became synonymous with Mercer heating, regardless of whether the specific implementation matched Thomas's techniques exactly. Settlers shopping for land or evaluating existing structures asked whether cabins had Mercer systems installed, treating it as a significant value consideration. By 1848, the technique had spread far enough that incoming settlers sometimes arrived already knowing about the concept, having heard descriptions from relatives or friends who had traveled through the region. The innovation had achieved self-sustaining propagation, passing from builder to builder without requiring Thomas's direct involvement. He had succeeded in solving a problem that affected frontier survival, and the solution had become part of the collective knowledge base that settlers used to adapt to harsh northern climates. Thomas Mercer left Dakota Territory in 1849, part of the broader migration westward that accelerated after gold discoveries in California. He was 38 years old, had saved modest wealth from a decade of successful trapping and farming, and wanted to establish a more permanent life than frontier existence offered. He traveled to western Oregon, purchased land in the Willamette Valley, and built a small farm where he raised cattle and grew wheat. He married in 1851 a widow named Catherine Ross, who had emigrated from Ohio with her parents. Thomas and Catherine had 3 children between 1852 and 1857. He never returned to Dakota Territory after leaving. His life in Oregon was quiet, productive, and unremarkable by frontier standards. He was known locally as a capable farmer and skilled carpenter who helped neighbors with building projects during slack seasons. Few people in Oregon knew about his time in Dakota or the heating innovation he had developed there. Thomas never mentioned it unless specifically asked about his frontier years, and even then he described it briefly as an experiment in cabin construction. He died on March 14, 1873, at age 62. The cause was pneumonia following a winter, respiratory illness. Catherine and his 3 adult children buried him in a cemetery outside Salem. His gravestone recorded his name, birth year, death year, and the simple inscription, "Beloved husband and father." No mention of Dakota Territory, underground heating systems, or the dozens of lives his innovation had made more comfortable and, in some cases, had saved outright. But in the northern territories, evidence of Thomas's work persisted long after his death. Abandoned cabins from the 1840s and 1850s, structures left behind as settlement patterns shifted and populations moved, still contained intact underground duct systems. When new settlers discovered these cabins decades later, they found warm floors even in winter when they built fires in the old fireplaces. The buried cedar logs, protected from rot by their natural oils, and the dry stone bases Thomas had designed, remained functional 30 and 40 years after installation. Archaeological surveys, conducted in the 20th century, identified multiple examples of frontier cabins with underground heating systems in Montana, Dakota, and Minnesota. Researchers initially struggled to understand what they were finding. Hollowed logs buried beneath cabin floors with connections to fireplace bases did not match any documented construction technique from standard frontier building practices. Only after consulting historical journals and letters from the 1840s did the pattern emerge. Multiple sources referenced Mercer heating or warm floor cabins, describing them as superior to standard construction but more labor-intensive to build. Modern thermal engineers who examined the surviving systems recognized sophisticated understanding of heat transfer and thermal mass principles. The designs demonstrated knowledge that was uncommon even among trained builders of that era. The fact that a frontier trapper with no formal engineering education had developed and successfully implemented these principles impressed researchers familiar with the challenges of passive heating system design. Thomas had solved complex thermodynamic problems through observation, experimentation, and practical application of basic physical principles. The legacy Thomas left was not recorded in books or celebrated in public recognition. It existed in the physical structures scattered across thousands of square miles of northern frontier. It survived in the warm cabins that protected families during brutal winters. It persisted in the knowledge passed between builders across generations.